Now, if we focus on the width and height, we print the shape here. And again, we focus on that 11 by 9 in this 11 by 9 grid cell. If we extract the values of the width and height, this is what we obtain. Now, you can see that the formula here for the width and the height is different from the x and y coordinates. In this case, we're multiplying by 2 as before, but we're not subtracting anything, and instead we're doing the square of that, and then we're multiplying by the predefined width and height. That is anchor 1, the width 156, and the height 198. That's what the PW 156 and 198 PH. So we multiply that by 2 times the output of the sigmoid that has been squared before. So if we perform this operation first, meaning multiply by 2 and then the square of that, then these are the values. And then when we get the anchor grid for that anchor 1 and grid cell, this is the value, the 156 by 198. As you can see, anchor grid has all these values, but we're only using right now that one because we're focusing on that anchor grid and that grid cell. So when we perform that multiplication, the value of the width is 425 pixels and the value of the height is 217 pixels. And these are already dimensioned according to the 640 by 640 image. So basically we have the pixel values of the center point of the bounding box, as well as the pixel values of the width and height respectively. So if we want to show that visually, what we can do is convert, and we'll do this later as well, but I wanted to show it here in this section. We can convert that x and y and width and height to x and y of the top left corner of the bounding box and x and y of the bottom right corner of that bounding box. So this is extremely easy. We have the center, so the top left corner will be x minus half of the width, and then same with the y component of the top left corner will be y minus half of the height, and the bottom right will be x plus half of the width and y plus half of the height. When we run this function, and then here we input our x, y, width, and height, removing one dimension, we input into this function here at the top, which if we plot it in this helper function, we obtain the bounding box of our prediction. And this is mostly it. Later in the next section, we'll formalize this operation, but this is, for the most part, what is happening, where the sigmoid output of x and y gets processed by this function here, and the output of the width and height gets calculated with this formula, and the values correspond to already the bounding box prediction. So we are almost there. And to conclude this section, I just want to show you how the shapes got changed through the process. And I'll focus on index 2. We went from 1024 by 20 by 20, 1024 by 20 by 20. We convolved that to obtain 255 by 20 by 20. These got reshaped with that view to 1 by 3 by 20 by 20 by 85. See, this is 3 times 85. So we unwrapped the anchor, and for each of the anchors, we obtain the 85 values for each anchor. These 85 values for each anchor. And then we use those values to calculate the sigmoid. So here, if I run this, x and y, as well as width and height and conv, will be created. And then here we're performing that operation for x and y times 2 plus that offset, that negative 0.5, and the corresponding relative coordinates of each grid cell, times the stride to scale it to the 640 by 640 image. And then for the width and height, we did this formula, and then we apply the anchor grid to scale it as well. By the way, the formula for the height and width also got modified. In previous versions of YOLO, it was simply the exponential, which is very dangerous, as Glenn Jocker points out, and this can lead to gradient issues, instabilities, and even loss of training. Because if you're performing the exponential of the input, if the input is very large, then you're going to have issues there. So with the formula that he developed, he's constraining the output so that if TW is 0, then this will be 0. And if TW is 1, which is the maximum value of the sigmoid, then the output would be 4. So you can see it's constrained between values from 0 all the way to 4. And this in contrast with the low end 0, but no clear upper end boundary. So this is very dangerous, and he got it solved with this formula right here. So he has modified the X and Y formula as well as the width and height formula for better predictions. So here, once we perform these operations for X and Y and width and height, we concatenate it back. So here we split it, here we split it, we perform the operations for X and Y, width and height. We didn't do anything for the conf just yet. And then we concatenate it back along the 4th dimension. We concatenate it back into Y. And this brings us to here, where it's concatenated. And then Y that view changes that shape to 1 by 3 by 20 by 20 by 85. So we basically combine these 3 dimensions into 1 for a total of 1,200. 20 by 20 by 3 is 1,200. And we have 85 values for each of these grid cell predictions. And then Z here at the bottom, once we run this. So what's going to happen is Z, once we return all of this, would be right here. And given that this is false, we're going to output this tuple towards that cat, where Z will be concatenated along the dimension 1. So basically, all of this, which is right now a list, you see Z is a list of 3 tensors. And for example, this one, you can see the 1 by 1200 by 85, this one right here, and the same with the other ones. We concatenate them along dimension 1, and this is the output. And then we're also passing along the values of X. So the values of X also will be passed along to the function that call this forward method. So when I run this, now we're back to base model. And then when I run this, X will be modified and we'll have that tuple of this component as well the X of the 3 X's, 3 inputs. So when I run that, and now when I run this, we'll be returning X to this forward ones method inside the section model. So when I run this, we'll return that to the detect multi-backend class where we call it from. So when I run that, now we're here. In this case, Y is a tuple. And now the moment I run this, the pred function has been created, which has the Z value of 1 by 25,200 by 85, which is this one right here, and the X values as well.